we're staying in AD4GD. I want to show you something what we found out at our pilot 1. That's all about small lakes in Berlin. A little background on why we did what we did. So here you can see a map of Berlin, but it's not the usual map. It's a map of only the small lakes. And as you can see here, there's more than 400 of them. So it's a huge number. We know there's high value of the lakes, so we have them as recreational area, biodiversity hotspots. They reduce heat islands and so on. So they improve the quality of living. But there are no regulations to monitor them. And the lake managers, which are the districts in Berlin, they don't have the capacity. So there's a huge knowledge gap. And in AD4GD, we promised 3 different things. First, we wanted to give the existing data that we find an added value. So which data is already available, but maybe not really used. We secondly want to create new data. And then in the end, we want to combine it all to have efficient data analysis that can be used for decision-making in the end. And of course, regarding the project, we want to provide data for the AD4GD data pipelines. And then the last step, of course, we also would like to benefit from that and use it again to combine the data. This is how it might look like if there's a lake manager and sees a small lake on the map and knows nothing about it. And then this is just an example. There are several questions. What is the water quality? Are there any fluctuations of the water level? Did the water quality change recently, and how is it used? Are there, for example, dogs swimming in the lake? No one knows. What is the biotope around there? Is it important, maybe for urbanized? And if I want to improve the situation for the lake, what are the right measures to take? So this is what we wanted to answer. And fortunately, there are many different potential data sources. I don't want to mention them all here, but some of them are like everywhere available. That's like satellite data and meteorological data, while others like water level are only measured in some of the larger lakes. We have, of course, science research data that sometimes focus on one lake in much detail, but no one ever really uses this data because it's so hard to get. It's some report or no one can find it. And then we have data from the districts. They don't share the data. And then, of course, many citizens who know their lakes maybe best, or NGOs that really know the lakes very good. So many things to try out. We've tried out many things, but I can only show you 2.5 now. So the first one is the first point, giving existing data added value. And we tried to use satellite data to estimate the trophic state. A very, very short theoretical background on the trophic state. What is measured is phosphorus, the visibility depth, and the chlorophyll A content of the water. And this is done throughout the summer season. So from April to October in Germany, once per month. And then it's aggregated and you get a seasonal value. So the trophic index or trophic state is something that is not defined for one step in time. It's defined for the whole season, which is not very common in satellite image processing, maybe. Then you use all this data, you have some equations, some deterministic equations, and you get a trophic index, which is from low nutrients, low chlorophyll A, this is basically clear water, good water quality, until this oligotrophic, so the blue color, you will see the colors again. So, and then it goes from over green to orange and purple, which is hypertrophic, the opposite, bad water quality, so high nutrient content. Less oxygen there. And what we did first, as I said, we don't have any data for the Berlin lakes. That's a problem. But fortunately, around Berlin, there's Brandenburg, which has a lot of lakes, and they do the monitoring because they are larger and they need to do it according to the Water Framework Directive. So we could find lakes that have a very low trophic state and lakes with a very high trophic state. And we have looked at the reflectance of the different bands from the Sentinel-2 mission. And if you have got enough time to look at it in detail, you find that there is the band number 5, which is this one in the orange rectangle. increases when the trophic state increases, the band number 2 decreases when the trophic state decreases, and this, so we defined our trophic index, just we gave it a shot and defined the normalized difference trophic index, which is it's like the common way for this satellite-based images, and it is below zero if there's a low trophic state, and it's above 0 if there's a high trophic state. We also compared it to already existing other indices, but in the end, this was the one that performed best. And here you can see one correlation. In total, we had 294 lakes in Brandenburg, for which we had data for 5 years, and we did a correlation for each year. It's a simple linear regression thing. And we did the Pearson correlation, and you can see for each year it's varying a little, but there's a strong correlation for each year in the end. So our conclusion was, yes, we can use it to estimate the trophic state of a lake. And now there's one example for a small Berlin lake now. The first thing that is happening here is we need to, so we have this polygon of the lake, and we only want to use pixels of the lake which are higher than or more than 80% in the year classified as water according to the scene classification. For the other pixels, we say, oh, the quality is not high enough. Who knows what is happening there? Let's not use it. So we only use those high water quality pictures or pixels, and then we get this this index for the whole year. So this is for the year 2018. And in the end, we got a distribution of pixels. And for the whole lake, we choose the one that is on the maximum of the density function. So what we get in the end, we get 3 values. We get a trophic state for each lake where we have enough pixels, of course. But we can also get short-term trends and long-term trends with this, which was really important, because if you are a lake manager, you want to know if some water quality, if it might decrease or not. And here's one example. On the left side, you can see the Obersee, which is the hypertrophic, so the highest polluted lake of our lakes that we were able to assess. And on the other side, it's the lowest polluted lake. And a funny thing, I've looked up the Obersee in Google Maps, and I've seen that it is marked as open toilet. I'm not sure if this has something to do with this. So maybe someone should remove this.
Maybe that's why it's so bad. Maybe that's the reason why.
So yeah,
It's
makes sense.
hypertrophic.
It's hypertrophic now. So that's the first result. We have developed this using the Brandenburg lakes, large lakes. A high correlation was found. We have then added a Jupyter notebook. Maybe I can show it to you very briefly. It's in the AD4GD GitHub account. And what it does, it implements the whole processing steps and then runs it on the OpenEO platform, so that we don't need to do it locally. And I've seen for this picture that you have just seen, the example, it was 4 GB processing on OpenEO, but our GeoTIFF at the end is only 180 kilobytes. So, okay.
A quick question before you move on. Can this analysis method based on Earth observation data allow the city of Berlin not to take the measurements and to save money and to rely on the satellite data?
This is actually what we are discussing with the Brandenburg Environmental Agency, because they need to do the measurements, but still they want to continue to do this, but they think about using it now to include smaller lakes and to have a higher temporal resolution, because the in situ measurements are only done every 3 years.
Oh, okay.
Now they can improve their knowledge.
Thanks.
Then we promised to create new data, and we have done this, amongst others, by using citizen science. For this, we have adjusted the CrowdWater app, which is an app by the University of Zurich. and it was meant to be for small rivers, but we have adjusted it so that it can be used for small lakes now as well. You can see a map of Berlin with different sites that are already implemented, and that to understand how it works, there's like very simple questions like, would you swim in the water, or how deep can you see? And then you have some qualitative answers that you can choose. But we have added those answers, thanks to Victoria, to the Rainbow server. So it's very precisely specified now, not only the question, but also the potential answers, so that you can, what I will show you next, can be done independently by the app now. But of course, it's nice for us. We've got this online database that we don't need to care about. We can just download the data and use it. So all the questions that are asked, we ask them for a reason. And in the end, if we ask for the watercolor, we think if someone answers it's very green, then probably there's a lot of algae, which means there's a lot of nutrients and so on. So we can derive some indicators using the answers of the CrowdWater effort. Here's one example. In the end, we do this automatically. The CrowdWater indicator nutrients. We have positive impacts, or positive means low nutrients. If you answer you want to go swim there, then probably it's clear water. It doesn't smell. It's good. So it's positive for the nutrient assessment. On the other side, a negative example would be like water smells like sewage or rotten eggs. It gets a negative value, and you sum it all up, and you get a range from -5 to +6. And we would expect a lake that is -5 that probably has a high nutrient concentration, and the other way around. And here you can see two examples, extreme examples now. On the right-hand side, probably you would have guessed already that there's more nutrients in there. It's very green on the surface. You cannot even see the water. There's so much duckweed on it. And so here is the difference from 5 to -5 in the nutrient indicator. But what you can also see, there's only one observation record. In the end, it would be much nicer to have more and have some kind of average value that's more robust than having one value from winter and one from the summer, and who knows if it's comparable. But we have not only done this for those two lakes, but for more than 200 lakes now in the whole city of Berlin. And so it's now very easy for someone who wants to have a brief screening of all the lakes to see, where would we suspect now high nutrient lakes or not so much. And of course, citizens and NGO can do it, but also the lake managers themselves could go there to the lake, answer all the questions, and get the indicator in the end as some kind of standardized method. Yeah, this is the half example I want to show. Another indicator is the water availability. In the left picture, you see a forest, but if you look on the map, this should be this lake. So apparently there is no water there. And this is, of course, added to the observation in the CrowdWater app. So this will give a negative score of the water availability indicator, and you see, there might be a problematic lake. And then we have another index, which we call stormwater inflow potential, and I to show you very, very briefly how it works. Yeah, there's the lake. You have simply drawn a buffer around the lake, 200 meters, and then looked at the surfaces here and how much stormwater runoff they produce. And only the red ones produce a certain amount of stormwater runoff. So you can see here, okay, this lake doesn't have any water, but probably stormwater is not the right solution. So you need to think for something else, or at least the stormwater in the surrounding area. And this is pretty much it, because combining data, this is the splashboard. I don't know if you have seen this presentation before from Christian, but this is, of course, somehow the final product where it all comes together. So the idea was to put the lake in the center of all the data and collect or relate all the data that we find to this lake, not only the raw data, but also all the indices that we have developed now. And maybe I can just end the presentation with a view on this. Cannot do it.
George, be prepared because we need to run with it.
Yes.
Okay. Sorry. Not possible.
No? You can show it with some beer
Yeah. So maybe
on the river.
maybe at the very end I had some open questions because I mean AD4GD is over now, and I have learned a lot about harmonization and semantic uplifting. I've never done this before, metadata so much, but there are still some open questions now for me. So, for example, how can I, as a researcher, add, I'm not sure if it's the right word, add data to the data space? What about the process data? So how do I add the indices that we have developed? And what about data from other persons? In Berlin, we have this, or third parties, we have this Wasserportal data. Would I be able, because it's open data, would I be able to relate this to the data space so that it's part of the data space, even if I didn't produce the data? So have some kind of community that feeds the data space? Things like this.
It really depends on the governments. Now we can do whatever we want because we are experimenting. But at some point, with the governance rules, those experiments will be removed and the serious thing will start. So the serious business. So probably the second you will not. For the first one, I don't see why not. I hope that we establish the governance rules that allow for these kind of things. No.
I think all of that is possible, and the responsibility is the data providers. So they have to be responsible for the data.
Mm.
That's the key thing. So you cannot randomly put stuff in. If it's open data, I don't have a picture, but I don't see this as if it's truly open data, our intent in stage is to make it accessible via APIs. So the only issue will be, is there any sensitive data there? And if there is not, it should be something that is directly accessible and identifiable in our catalog as a data source.
Mm-hmm.